Hello, so this is chapter 4, Streamflow measurement. Okay, so for this chapter will be some introduction, just a recap on how it is related, water level measurement, gauging site, and stream flow measurement. Okay, so there are two main methods actually, which is float method, okay, and the velocity area method. Okay, the current meter is actually used for the velocity area method, and also indirect method is just more information on how do we measure the stream flow measurement. So actually there are three kinds of how do we measure stream flow: the float, the velocity area method, and some indirect method. Okay, just for recap, remember hydrologic cycle. So delta S is the groundwater. Okay, it's the groundwater storage. Remember we have precipitation, rainfall, we have evaporation, transpiration, and infiltration. Okay, here this use ETF. So we have runoff. So this runoff excess water. So this is what contributes to the flow rate for the hydrograph. So but actually for hydrograph we have a base flow and the runoff. The base flow, which is if there is no storm, and if there is some storm, then we will have some runoff water or excess water. So what we want to measure here is all the hydrograph, the flow rate, the base flow, and also the storm during storm event. So it usually is a continuation, a continuous data. So I always draw this kind of figure. So it's a catchment. So this is a catchment. Okay, so it's a catchment, and the catchment will have some river. So usually we will observe the discharge at the downstream. Okay, so this discharge may be measured by a river gauging station or a water level station. It may be a river gauging station which measure discharge, or it may measure water level. If it measures water level, then we need to have a rating curve. Okay, so rating curve is a curve which translate water level to discharge. Okay, so whatever it is, we need to have some kind of a water level or discharge station at the downstream. And this is to monitor the flow within the catchment. Okay, so this is a typical water level station. This one is taken from the Department of Irrigation and Drainage manual. So there are some elevated station and on ground level station. So it actually this is actually beside rivers, so that it can measure the water level of the river. Okay, so there are many kind of instruments how they measure the water level. This is another water level telemetry station near a river. This is in Sungai Kuantan at Bukit Kenau. So this is also the Department of Irrigation and Drainage station. In Malaysia, usually it is from the Department of Irrigation and Drainage. They have a lot of water level station network, and because they are the one who monitor the drainage of Malaysia. So usually the water level station are owned by them. So there are many kinds of how it measures the water level. For example, staff gauge, but this of course should be recorded by human manually. And there are also some automatic water level recorder, mechanical and digital. So you may read about this more in another notes or the manual of the Department of Irrigation and Drainage, just to show that there are continuous data of water level recorded. This is also some example. This is, I think, more like indirect. They have this automatic water depth measurement, and then using some mathematical formula, we can get the discharge, the stream flow value, using some mathematical formula. So we will see on that later. So just for recap, stream flow gauging is just to determine the amount of water at the outlet point or at any point of the river, just as the same figure that I showed with the catchment. And again, if the station measure the water level in meter, so they should have some kind of a rating curve to translate the water level in meter to discharge value, which is in meter cube per second. So where is the most stable gauging site to put our water level monitoring? And also we need to do some gauging, means that we need to develop this stage discharge curve. So there are some requirements or guidelines on where to put this. So for example, it should have a well-defined cross section which does not change in various seasons. Okay, it should be easily accessible. Okay, the site should be in a straight and stable reach. Reach means river. The gauging site should be free from backwater effects in the channel. So we don't want some other source of velocity or velocity mostly, which we call it some backwater effects due to some structure upstream, or some how do you say it, pantulan from other structures. So we don't want that. So again, the stream flow should be straight flow. Okay, no backwater, at straight river section. Okay, and not at a meander. Not at a meander. Meander means like a curved river, not at a meander. Okay, so we have a float method, and we have a area velocity method, and the indirect method. Okay, so for more additional information, you may find or read more into like dilution method or electromagnetic method and ultrasonic method. But for our chapter, we will focus on float, area velocity method, and also indirect method. Okay, for the first float method, okay, so this method is, as far as I know, is not usually used here, but it's just some alternative of measurement for a fast measurement. Okay, so what they do is usually ideally we need 3 cross sections, one at the beginning of the reach means river, one midway, and one at the end of the reach. So the beginning, middle, and end, but depending on set conditions, the midway section is sometimes omitted, because remember, if you want to measure this, we need to have a straight river. It's not meander, a straight river, no backwater. So sometimes it's difficult to find the right section for measuring it. Okay, okay, this is just some more guideline. A travel time of at least 20 seconds is recommended. Travel time of at least 20 seconds is recommended, but a shorter time may be used for streams with high velocities, when it may not be possible to find a straight reach of channel having adequate length. So what this travel time means is that we put the float and we release the float. So we need to capture how far or what is the distance of the travel and what is the time from point 1 to point 2. So so this is what it means by the travel time, at least 20 seconds. But if it's a really fast high velocity stream, so maybe we don't need 20 seconds, but maybe we may have more or less time for measurement. Okay, there is also a guide where the distance between the upstream and downstream cross-section should be about 4 or 5 times the width of the midway section or the average of the river. Okay, this is just a guideline. It means that, let's say this is the river. So the upstream and downstream, okay, upstream and downstream, up and down. So okay, this length should be at least about 4 or 5 times the width. 4 or 5 times the width. This is the width of the river, or the average width of the river. This is just a guide. The surface float is the simplest form of flow, although it is influenced by wind. And nevertheless, this type of float is available when quick measurements are needed. So there are many types of float: canister float, or rod floats. So let's see the example. Okay, for example, a canister float, or this is surface float. A canister float, it has some weight inside, and also some rod float. So they are designed so that they extend through as much of the stream depth as possible without the lower end touching the bed. Okay, so these are floats, terapung. And then we measure the time, and we measure this distance they travel. So then we may get the Q, the velocity, using the cross section, okay, and the velocity. Okay, so what is the cross section area and the velocity? So let's say okay, you need to imagine this way. So let's say this is point upstream. Remember the upstream. So you release the float and it goes to the stream to downstream. Okay, so downstream. So you may estimate this area cross section. You can estimate this area cross section. That's why for it to have a more accurate, you need to have a straight ridge or straight river, and the area or cross section has not so much difference across the line. So that is how you measure the Q using the float method. So you divide them by some section, okay, and what is the cross section, the A, and what is the velocity, and then you average them and you will get the Q. Okay, so we go into velocity area method. So this is the most used way, even in the consultation or where we want to measure the discharge, the flow rate of a river. So this is the most used method, which is the velocity area method. So this method uses the current meter. Okay, so we need to have a current meter for measuring the velocity. So there are a lot of types, like a propeller type. This is cup type. I think for me personally, we never use this cup type, but for propeller type, we always use propeller type, and also some sensor type. So this one is using transducer or electrical method or sensor. So propeller type might have its limitation also. For example, if there is some small vortex, the propeller might not work really better than digital or sensor type. Okay, but of course it depends on your budget, your which one. So usually digital or sensor type are more expensive than the propeller type. Okay, so because river, this is river cross section and this is the water depth. So because if the depth is deep, it's not a shallow depth, it's deep, so you may differentiate the velocity, because the velocity is related to the depth of water. So if the water is shallow, you may just take the 0.6 d. So d is the water, the river depth. just one reading you may use for shallow depth. Let's say this red color is for shallow water level 0.60. But if it is a deep water, so you may need to measure 2 points, 0.2D and 0.8D. Okay, okay, this is the water depth. Okay, again the description, if it's a shallow water depth, you may measure the velocity 0.6D from the surface, and if it's a deep water 0.2D and 0.8D. Okay, so we know the velocity at several cross sections. So later we need to average the velocity, and afterwards what you want to find is actually the flow rate. So you need to multiply the velocity and the area cross section. So the simplest way is, what is the velocity of this water flowing, and what is the area? So you just multiply it, so you get discharge. Okay, so again, because the river is really wide, so it's not really accurate if you just measure 1 point. So you will need to divide the river into large number of subsections vertically. Okay, and we take the average velocity in these subsections by using current meter, okay, or floats. Float is if you use the previous method. Okay, but this is for the velocity area method. Usually we use the current meter. It actually relates. It has some similarity actually. You just need to find the velocity and area. That's all. Okay, the accuracy of discharge estimation increase with the number of subsections used. So what is these subsections? Okay, so how do we define these subsections? How many subsections or segments? Segments or subsections. So it should not be greater than 1/15 to 1/20 of the width of the river. This is just a guideline. The discharge in each segment should be less than 10% of the total discharge. The difference of velocities in adjacent segments should not be more than 20%. For natural river, the verticals for velocity measurement are not necessarily equally spaced. It doesn't, the sections, let's say this is the river, okay, and you make the section, so it doesn't not have to be vertically equally spaced. It may be some width is larger than some other segments width. Okay, so this is the example of the subsections, like this one, this line. Okay, so these are the subsection M, P, R, okay, S, T. So these are the lines which divide the river into subsections. So this green dot is the current meter or the velocity measurements. So this is a deep water level river. So we measure 2 points. So there are two things here. We need to know the cross section area. So this is the cross section area. Okay, for section MP. Okay, and this is the cross section area for section PR. Okay, and so on. Okay, so for each cross section we have this velocity measurement using a current meter. For this case, for this method, we use the current meter to measure the velocity. So we have two things: the velocity and the area. Okay, so to measure measure the cross section, there are two methods, and one of them is mid section method. So what do this mid section means is that how do we calculate the area? Okay, so for mid section method, the area is calculated by multiplying this width, okay, to this depth. So the depth is in the middle of the cross section or the segment or subsection. So this is the first subsection or the first segment. Okay, so how do we measure the area for the segment is B1, okay, multiplied by the mid. That is why we call it mid section, the middle depth, D1. Okay, and so on. For area 2, for area 2, okay, so these are the sections. Okay, so B multiplied by this depth. So the depth is in the middle, in the mid of the section, and so on. For B3 and for area 3 and for area 4 is the same method. So let's say we already have these velocity measurements. Okay, these are the velocity measurements. So you may, if this area does not have velocity, so you may neglect this area. You may discard this area. So what you do is for constructed line to divide mid-section panel. Panel 1, V1, A1, panel 2, V2, A2, panel 3, V3, A3, panel 4, V4, A4. This panel actually means segments or the subsection. Okay, it's the same thing. Okay, so for each velocity, okay, because at one subsection we have 2 readings. Okay, so for this section we have 2 readings, so we just average the readings. For V2 you have 2 readings, just average them, and so on. Okay, so you know the area A1 and you know the V1. Okay, so you know the A1, you know the V1. For all of the sections or the segments, so then you just total it and don't average it. You need to total it to add them all, because this is one section, this is second section, third and fourth. So what we want is the flow is meter cube per second. So don't average them, we need to total them all. We need to get the total of the volume of this cross section. So add them all, total. Okay, so there's another way, okay, where using the mean section method. So this one, remember, before the line is like this way. Okay, the mid section, the line is this way. Okay, but now we are using the mean section method. So the mean section method is the line, or the line separating the segment is this way. Okay, it's on the observation of the velocity data. So this is MPRSTU. Okay, before it's in the middle, in the mid, but now it's on the same line as the what I mean, the same line is the same line as in the velocity measurement. So this we call this the mean section method, MEN, mean. So how do we calculate using the mean section method? Okay, is this way. So for the area, for this area, for the first area segment is this one. Okay, this is the first segment. So what you do is you need to get the width, okay, from the bank atau tebing bank to the observation line of the velocity. Okay, so the area is you use the trapezoidal formula, half multiplied by the depth multiplied by the width, by the depth and by the width. So you get this, the area 1, A1. Okay, and then A2, the same thing, okay, using the trapezoid formula. So you get so this one, W2, okay, multiplied by D1 plus D2. Okay, D1 plus D2. and then divide by 2. So this is it's like a trapezoidal. This is trapezoidal, right? So you have D2, you have D1, you have W1. So if you want to get this area, so it's a trapezoidal formula. Half multiply by D1 plus D2, okay, and multiply by W1. So this is for the mean section method. So this is for the area. So for area 3, area 4, and area 5, okay, use the same formula. Okay, so to measure the velocity, so for the velocity, for example, velocity 1, 0. Okay, let's say, because one line should be here. So for velocity, okay, this is the second line. So velocity is 0. This velocity is 0, right? Plus this average of this section, okay, and then the average divide by 2. Okay, so for the V2, so V2 is actually here, right? This is V2. So now we have two readings of the velocity, two lines of reading, this line and this line. So what you do is you average, okay, 0.22 plus here 0.22 plus 0.18, you average them, okay, and then you add plus 0.24 plus 0.16, and you average them. So from this you average them all, so that is why you get this formula. Okay, so on V3, V4, and V5. Okay, so for mean section method, so in the end you just multiply A and V. Okay, and finally, when you get the flow rate for each section, so this section means this 1, 2, 3, 4, and 5 section. So it has its own A1, V1. It has its own A1, V1, A2, V2, and so on. So you add them all. Okay? Same like the mid section method. So then in the end, finally you will get the Q for you will get the Q, okay, for this whole cross section. Okay, so we have some exercise. So you try to do this exercise, and we will discuss when we meet. Okay, next we have this indirect method. So what is this? Okay, under this category included those methods which make use of the relationship between flow, discharge, and depths at specified locations. The field measurement is restricted to the measurement of these depths only. Again, the value recorded is just the depth. Okay, using structures like notch, weirs, flumes, and sluice gates for flow measurement in hydraulic laboratory is well known. Okay, so this means that, okay, this type of structures like weirs, flumes, sluice gates, they all measure just the depth, not the river depth, but some kind of depth from the river. So there is some mathematical formula which converts this flow depth into which converts this water level into flow. Before, if we use the time area method, not time area method, the velocity area method, we use the current meter, right? But for this method, we use the river depth. For example, there is a river or open channel, and then we put some gate, or a weir. Okay, this is some, let's say it's more simple, this is like a V notch. So from V notch, we know some depth, this river, and we know how much the depth of the depth of the water level, okay, as it flows through the V notch. So there is some depth here, okay, in meter. So using some mathematical formula, we can convert this depth into velocity. So this is usually used in hydraulic laboratories to measure the flow. Okay, these conventional structures are also used in field condition, but their use is limited by the range of head. Head means, let's say this is the river. Okay, and then this is the structure, the hydraulic structure. It may be a V-notch or a weir. So it depends on the head. Head means, let's say, let me use another color. This is the V-notch. V-notch or weir, okay. So, and then there will be some water. Okay, so this head is this depth, the small depth between the structure and the water level. So it depends on this range of head, debris or sediment load of the stream, whether it is suitable to be used at site. To overcome many of these limitations, a wide variety of flow measuring structures with specific advantages are in use. So this is actually for this kind of method, it is related, or it may be impacted from, like, for example, sediment load, debris. Okay, so there are some methods they use to avoid this. Okay, so for example, if you use some weir or similar flow measuring structures, do you know here? Weir is, okay, this is, how do I draw it? This is the river. So there is some structure which increase the elevation of the bed. Okay, so that they can measure the head of the water level, and then from that head, they can find a Q using some formula which is established formula or functions. Okay, so these structures, the discharge Q is a function of the water surface elevation measured at specified upstream location. Okay, remember the elevation, the water elevation or water depth, and then they use some formula to determine the Q. Okay. So there are some categories of these flow measuring structures. Thin plate structures, usually made from a vertically set metal plate. Okay, for example, the V-notch. The V-notch, rectangular, full width and contracted notches, and typical examples are typical examples under this category. And there is also some long base weirs, also known as broad crested weirs, are made of concrete or machinery and are used for large discharge values. Okay, and flumes are made of concrete, machinery or metal sheets depending on their use and location. They depend primarily on the width constriction to produce a control section. So for example, number one is thin plate, like I draw for you, like this is the cross section, and then there is some thin plate with a V-notch. This is some V-notch, and then there is some weir. Let's say there is the river. If you look above the river, and there is some broad crested weir. Okay, so this one which it limits, if we look it sideways, how do we draw sideways? Let's say this is the river of the bed, so we have some weir. Okay, and then this is the flow of water, and then this is the water level. So there is some, we reduce the depth, so that we can estimate the velocity from our formula of the depth. And also there is some flumes which is constricted like this way. If we look above, let's say this is the original river, so it may have some constriction. Okay, something like that. Does this make sense? Wait. Say this is the original river, so they constrict the river width like this. For example lah. So this is width constriction. There are several structures. Okay, like I told you, using some mathematical formula. Okay, these are established mathematical formula. For example, for weir, okay, for V-notch, okay. So let's say this is the water level. So the head, what is the head? So the head might be this one, if I'm not mistaken. Okay, so this is the water level. So this head. Okay, so from this formula we can estimate the Q. Okay, so this one, river rating curve, I already showed you the rating curve. So it also determines the relationship between the water level and discharge. So this kind of method, river rating curve, this one you need to do some experimental study to find this relationship, to find this formula. You have to do some river gauging. Okay, so observation at site, so then you will get this what formula, what is the A, what is the B. So recap, so for rating curve you need to have water level. Okay, it's continuous water level data. So let's say you have the H and you have the Q data from site observation. So these are the data you have. So you need to plot the H versus Q, or Q versus H, it doesn't matter, and then you create your formula, okay, to make the relationship between H and Q. Okay, so usually the rating curve is a curve, but if you log it, you may get this linear regression curve. So from linear regression curve, it's more easier for you to get the parameter A and B. Okay, so A log A is the what do you call, pintasan Y, on the y-axis intersection, and B is the slope. So from if you log it, then you will get a straight linear regression line, and then you can get the value of A and B. Okay, but now you have Excel. Okay, there is computer assistance like using Excel. You can get this curve line. Okay, it may look the line might be like this or like this, so it depends on your flow. Usually it's like this, if I'm not mistaken. So then you can just use Excel to get what is the equation, y equals to what, the equation of the lines. Okay, or you can use log to get A and B. This is if you calculate manually. Okay, if you calculate manually on paper, you can log Q and log H, and then you get the relationship and you get the formula. Okay, so this is an example. Let's say you have the water level data, the height, and you have the discharge. So you can plot it manually using hand, or you can do it using Excel. Okay, so when you plot, you have this relationship, and you see that it is a curve. If you use Excel, you just take the add trend line, add trend line. So you want to get the formula y equals to what, x square plus what, so get this formula. So when you get this formula, you actually get the formula of the relationship between H and Q. Okay, but as I showed you before, you can also plot it manually. So what you do, if you get a curved line, you convert it into a straight line. How do you convert it? You log it. You log H and you log Q. Okay, you log H and you log Q, so you will get a straight line, a linear regression line, and you can get the y intersection, and you can get the slope. So then you can create your formula. Okay, so this is another example. You have the water level, height, and you have the discharge. So you notice when the height of water level is 4.42, your discharge is 3.19.79. Okay, so when it is 5.33, this is your discharge. So these are all observation data. Okay, so what you want to do is you want to find this relationship. Okay, so how do you do this is okay, because you want to find the curve Q and then this H, so you want to find this from 0 when the Q is 0. So you need to multiply, not multiply, divide divide minus. So minus your data H to H naught. So H naught is when Q is 0. Okay, H naught is when Q is 0. So actually this one, you know what is Q when it's 0. So it means that this is the river. So what is this elevation? So that is H naught. And what is the most lower elevation? Okay, so just if you want to produce this formula, okay, so what you do is log Q, log everything, log Q equals log A plus B. Okay, because if you do log, B comes in front, so B log. So this one, because you want from Q equals to 0, so you must minus H naught. Okay, so for this example, you know, we give you lah, for this example H naught is 1.6. Okay, so that's why you minus 1.6. So this is the Q that you observe. Yeah, then you log them. Okay, log. Then you plot log Q against log H. Then you get this formula. Okay, so you get this formula. So you know log A is 1.78, A is 60.8, and B is 1.54. So you finally get this rating curve formula using the value that you get from this linear line of your log. So that's all for chapter 4 now. So thank you for watching.